Welcome back to another video about fluid mechanics. My name is Richard and I will be your SI leader for this video in the PHYS40B collection. Alright, let's begin. Just to recap, in the last video, we had shown this simple layout of the different fluid concepts categorized by their respective sections. We had a thorough session about pressure, hydrostatic pressure, and buoyancy, which is all entailed in fluid statics. If you guys have not seen this video, the link will be in the description below, and I highly recommend watching it before proceeding on into this video. In this video, we will primarily focus on fluid dynamics, or the study of fluids and motion. The two biggest concepts about fluid dynamics are the continuity equation and Bernoulli's equation. But before we move into these concepts, let us introduce a few basic definitions. Streamline is a set of curves or paths in which a moving fluid particle follows. In the image, we see the streamline of smoke traveling around a red vintage car. This model is recreating a scene as if the car was being driven against strong winds. There are three important properties when it comes to streamlines. 1. Streamlines never cross or intersect other streamlines. 2. At every instantaneous point in time along the streamline, the velocity of the moving fluid particle is tangent to the curve of the streamline. And 3. The separation or distance between two streamlines correlate to the velocity of the fluid particles. The second concept we will need to introduce to understand is volumetric flow rate. This is essentially the rate at which the volume of a fluid passes per unit time. The equation for volumetric flow rate is the product of velocity and cross-sectional area. Volumetric flow rate is denoted by a letter capital Q, so it cannot be confused with a velocity, which is a lowercase v. Let us now consider a pipe system where two pipes of varying diameter are connected by a joint as shown in the image. If, let's say, a fluid such as water travels from the left to the right pipe, we can draw what the streamline would look like. Assuming that the fluid is in laminar flow, this is the image of what we would expect the streamlines to look like. If I were to cut out two sections of each pipe in the pipe system, I need these two sections to be presumably the same volume. We had initially stated that the two pipes have different diameters, so the length of each section must be different in order to fill up the same volume of fluid. This can be visualized by the red sections in the image. Therefore, if these two sections have the same volume, they must also have the same volumetric flow rate, where Q1 is equal to Q2. As stated before, the equation for volumetric flow rate is the product of velocity of the fluid and cross-sectional area of the pipe. If we go back to the streamline of the pipe system, we stated that the more separation means smaller velocity. On the left pipe, we not only see this, but also recognize that the pipe has a much larger diameter and therefore a larger cross-sectional area. As for the right pipe, we can see that there is both a larger velocity of the fluid due to the compactness of the streamline and smaller diameter of the pipe. From here, we now know that there is an inverse relationship between velocity and cross-sectional area of the pipe, assuming a constant volumetric flow rate Q. One of the most fundamental principles in fluid dynamics is Bernoulli's equation. If you guys still remember the work energy principle, Bernoulli's equation is basically a derivation and application of it towards fluid mechanics. Although the derivation can be noted in the textbook, we want to first talk about what Bernoulli's equation actually means. This equation considers two distinct points lying on the same streamline, so we can solve for unknown values such as pressure, velocity, and height. If I have a system with a flowing fluid, I can choose 2 points. Within the system, these 2 points must have the same total pressure, which is denoted as capital P in the equation. Nearly identical to the conservation of mechanical energy from Physics 40A, we can see that there are three different types of pressure that contribute to the total pressure in the system. The first term in Bernoulli's equation is the external pressure, or lowercase p. This can be atmospheric pressure or pressure from an applied load, which is also force over area. We also have the third term, rho gh. The sum of these two terms should be familiar because it is an equation of hydrostatic pressure, as we had covered from the previous video. This is also referred to as the static pressure. The second term, 1/2 rho v squared, deals with the fluid in motion, which makes this the dynamic pressure in the equation. Now that we have talked about Bernoulli's equation, let's move on to an example. I have two schematics of a water tank, each with a hole at a different height. The first one has a hole at the very bottom, and the second has the hole at the halfway point of the water tank. The question is, which water tank has the fastest fluid flow at the hole? If you guys have already read the first section of chapter 14, you may have briefly seen an image similar to this as the example, and already know the answer, but may not know why. Water tank number 1 is now shown with 2 points. Point 1 is at the surface of the water and point 2 is at the hole. Before actually moving into Bernoulli's equation, we have to figure out what we know and what we want to know. Since point 1 has an open face and is exposed to the atmosphere, P1 is equal to the atmospheric pressure. It initially starts at rest, so the velocity at that point is 0, and the height is equal to h. At point 2, because water is flowing out of the hole and into the atmosphere, P2 is also atmospheric pressure. Velocity at the hole is what we need to find, so it is the unknown. And we know that height is 0. We can now start with Bernoulli's equation and plug in what we know. Once we solve and simplify, the velocity at the hole for the water tank can be determined, which is square root of 2gh. We repeat the same process with water tank number 2 as we did with the first one. As we see here, everything is basically the same, except for the height is now 1/2 of the original height for point 2. We can use Bernoulli's equation again and solve for velocity at the hole. And for the water tank, number 2, the velocity is the square root of gh. We can now look at and compare the two velocities at the holes. It is now clear that the velocities of water tank 1 is greater than that of the second one by a factor of square root of 2. I have also included an image of what the streamline of the water flowing out of the hole would look like, which should match the one in the textbook. Alright, so we have now finished all fluid mechanics. If you have any questions or concerns, feel free to comment down below or send us an email. Thank you for watching, and I'll see you guys next week. Take care.